All right, so this is day 3 of the 4th unit of the spring semester of pre-cal for seniors. So what we're going to do on this set of notes is I'm going to introduce you to what graphing looks like in the polar plane. So here are some 4 basic equations that we have. We have r equals 4. So that means that we have a circle of radius 4. So 1, 2, 3, 4, and you pretty much just have to sketch that 4th circle all the way around. And that's what r equals 4 looks like on the polar plane. Just the 4th circle, just trace it. Theta equals 30 degrees means that it's every radius point that's 30 degrees. So like all the positive radii would look like this. All the negative radii would look like this. So it ends up just being a diagonal line. And if you wanted to, you could convert it like what we did earlier and figure out what the slope of that line is. This next one, it's going to be more helpful if we do kind of convert it. R cosine theta is one of those conversion equations that we have that it's equal to x. So we have x equals 3. So if I ask you to graph x equals 3 on a coordinate plane, on the x and y rectangular plane, it would just be a straight up and down line at the tick mark of 3. What's very important about this in polar is that you understand that this line is tangent to the circle of radius 3. So just make sure that that line is on the outside of that circle when it only hits it once. So in class, what I would show you is kind of a Desmos activity on what this would look like and how we change things. You can maybe look it up or ask for the link on it. But what you end up doing and discovering with these different equations is that when you start changing that number on the outside of the trig function, you end up changing, and we call these roses, so we end up changing the length of the petal. So notice that with these polar equations, we have a number in front and a number inside. The number inside of those all stayed 2. What if I change that number on the inside from 1 to 3 to 5, but notice that I left the outside, say 6? Well, you'll end up noticing that with this rose, it changes the number of petals. But then you notice that 1, 3, 5 were odd numbers. So why did we do that? Well, let's look at the next one. We have 2, 4, and 6, which are all even numbers. So that does end up changing the number of petals. But if you notice that when you did 6 cosine 2 theta, you had 4 petals. If you did 6 cosine 4 theta, you had 8 petals. If you did 6 theta, you have 12 petals. So if n is even, then you have 2 times the number of petals. So that means if n is odd, then you only have n petals, because if you notice with this rose is you only had 1 petal, 3 petals, and 5 petals. What happens if you change the trig function from cosine to sine? Well, every single one of these petals started at 0 degrees if it was cosine. What happens is that you end up starting these kind of roses at 90 divided by n. So depending on what n is, changes where you start on the x-axis. So when I usually state this, I always usually say it starts off of the x-axis. Oops. So that's how I usually state that. All right. So how do we go about the steps of figuring out how to graph a rose? Well, you figure out what the length of the petals are. Find out how many petals there are. So again, if n is even, there are twice as many petals. If n is odd, you only have n petals. Cosine starts at 0 degrees, and sine of theta starts at 90 divided by n. And to figure out how all of the petals are spaced out, you take a full circle of 360 degrees and divide it by the petals, because that's how they're going to be evenly spaced. So what we're going to do is we're going to figure out the length of each of these petals. We're going to figure out the number of petals. We're going to figure out where it starts at, and the increments in which these petals are going to go. And I'm going to kind of show you how that I copy and paste this in sheet, because I'm going to use that again here in a little bit. So the length is the number in front of the trig function, so 3. The number of petals is based on the number that's inside of the trig function. So since we have 2 theta, that's 2 is even, so we're going to have twice as many petals. Since this is sine, we're going to start at 90 divided by n. N is the number that's being multiplied with theta, so 2. So we're going to start here at 45 degrees. So that means the first point I'm going to have is at 45 degrees with the length of 3. 1, 2, 3. That's where my first point is. That's where I'm going to start. Then my increments, well, I'm going to evenly space all 4 of these petals. So what I'm going to do is divide a circle into 4 sections, so 90 degrees. That means every 90 degrees I'm going to have a brand new point. So if I start at 45, if I add 90 to that, you get 135. Oops, that's not what 135 is. Here it is. And then 225, and then 315. And then with practice, you'll start being able to draw these petals out, but they just need to be nice and rounded. And it kind of, have some fun with it. They actually kind of look like flowers. Not really roses, but flowers. What about this next one? Well, again, we're going to find the same kind of information. So the length is a number in front. So the length of these petals are going to be 4. The number of petals is based on what's being multiplied with theta. That's 5. Since 5 is odd, we're going to have that many petals. We're starting with cosine. This is a cosine flower, so we're going to start at 0 degrees. So that means that my first point is going to be at 0 degrees and 4. So that's where it starts on the x-axis. Off the x-axis, you can notice that this previous flower did not even hit the x-axis. And then I'm going to evenly space all 5 petals. So I'm going to divide that by 360 and end up getting 72, which is not an angle that's on the unit circle. So you just want to approximate where 72 is. So here, and then 72 more is here, and then 72 more is like somewhere here, and then 72 more is somewhere here, and then you just draw your petals. The more petals you end up having, the thinner they are. We don't usually ask you to draw too many of them because that would kind of get crazy, but that's what that looks like. So, what about this next one? Well, this next one, it's kind of the same kind of steps. It's still a rose, but the thing is that the length of this petal is going to be 7 because that's in front. The number of petals, well, there's a 1 in front of the theta, so that's odd. So there's only going to be 1 petal. Since this is sine, we're going to start at 90 degrees divided by n, which is 1. So that means I'm going to start my graph at 90 degrees and go a length of 7. 1, 2, 3, 4, 5, 6, 7. And since there's only 1 petal, there's not going to be any need for an increment. So what does a 1 petal rose look like? Well, it looks like a circle. So if you went about converting this like what we did in the last set of notes, you can kind of figure out where the center of the circle is and the radius and all that stuff, like completing the square, or just realize that this is a single petal rose. The less the petals, the more circular they are. So I don't have to do all of that length and petals thing if I notice that it's just 6 cosine theta. It's a single petal rose. But the thing is, if I asked for 6 cosine theta, I would have started at 0 degrees. That negative sign kind of reflects it over the vertical axis. So you end up getting a point starting at 180 degrees. So 1, 2, 3, 4, 6. So you get a single petal rose, which is the exact same thing as a circle. So just make sure you recognize that. That's what a single petal rose looks like. It's a circle. If this was a -7 sine theta, it would have been a circle down here. Again, if this was +6 cosine, it would have started here. So these single petal roses start on an axis, depending on cosine or sine or positive or negative. Then this next graph is a pretty interesting graph. It's called the Leibniz gate. So in this class, the only thing that we're going to be changing is this a squared, the number in front of sine or cosine. Or I guess we are going to be changing cosine and sine as well. But the number that's going to change is a squared. This number on the inside has to be 2 theta, otherwise it's not a Leibniz gate. So in this problem here, they gave us that a squared equals 9. So if you square root both sides, you get a is 3. So just like roses, if we are going to give you a cosine, we're going to start on the x-axis. So since a is 3, I'm going to go here through the pole and then in this direction. Leibniz gates, in other words, are the infinity graph. So this literally looks like an infinity symbol. And there it is. That's what a Leibniz gate is. Again, the number in the front is going to change. So like this next one, we gave you 25. So a squared equals 25. So that means a is 5. The 2 theta has to be 2 theta. But if we change it from sine to cosine, what we're going to end up doing is starting at 90 divided by 2, so 45. So 1, 2, 3, 4, 5 at 45 degrees. Go in the opposite direction as well. And then you draw an infinity symbol. So this is what a Leibniz gate looks like. It's either going to start at 0 degrees or 45 degrees, depending on if it's cosine or sine, respectively. So have some fun drawing these out. We're going to do some more graphing next class, but have fun.